Good. So this is a totally interactive thing, and everything could be changed, and I hope it will be changed as we'll go, right? Because it's a small community of people, relatively advanced, and then which means that I kind of start from very low level, and which means that I assume that you have some basic knowledge, which you surely have much more, but and then I start moving very fast, and you can slow me down and say, yeah, or you can tell me, no, just jump over it and go next thing. Okay. And the mode, how we'll do it, namely, we can do it non-stop for like hour and something, or we can do 45, break 45, again, up to you. And if you, in the process, I'm here until the beginning of December. I'm staying now in Simon's, but Vadim is kind enough, so we booking hotel for me to come here regularly, so we can add lecture if we want that there's some materials that I'm not kind of want cover. You want to know more about this or about that, we can always add extra lecture at the end of November. Okay, good. So what it's all about? Goal is I want to show you several problems which are probably already well posed and aren't solved. So I'm talking to you as a researcher, to researchers, right? So it's less a kind of a usual teaching stuff. It's more just to show you to what extent what is turbulence theory and is somehow considered a little bit mysterious part of physics, or it's engineering, or it's mathematics, or it's some kind of obscure fluid mechanics. But what I will show you, this is part of theoretical physics and very closely connected to statistical physics and kinetics. That's why I'll start from classical kinetics, things that you know very well, and then I'll be moving and showing to what extent of something in turbulence is analogous or non-analogous. Generally, kinetics is about non-equilibrium, and turbulence we defined as a state of a system with many degrees of freedom extremely far from equilibrium. That's the definition of turbulence. You can have turbulence of water which runs somewhere. You can have turbulence of spin waves which you parametrically excite. You have turbulence of sea waves which you excite by wind. Okay, you can have turbulence of phonons which you excite in a pipe, like producing noise, or in a solid state. So turbulence understood as a very far from equilibrium state. So if you have few degrees of freedom deviated from equilibrium, like you run current, it's just non-equilibrium, but it's not turbulence. Turbulence is when you broke your detailed balance in an extreme way. So what you pump and what you dump are very far away. And there are many modes in between which are far from equilibrium. Physically, I'll be using over and over two things. Namely, we'll be always working with Hamiltonian systems. There will be Hamiltonian, which is a function of Pi and Qi, and they would run up to 10 to 23. So one system would be very familiar. It's just a set of particles interacting. So this would be Q, I, and J, and you have usual equation of motions, namely Pi dot is the derivative of Q Hamiltonian with respect to Q I, and your Qi dot is the derivative of Hamiltonian with respect to Pi. And what would allow me to treat this system very far from equilibrium is, of course, that this term would be considered in some sense much larger than this, namely that this will be limit of weak interaction, which essentially for us will be a limit of very short range interaction, so that this gas of particle will be considered very dilute. On the other side, I'll be working with a Hamiltonian written in terms of quasi-particles, let's say. So I'll be working in terms of just complex amplitudes, or if it will be quantum, there will be just AK dagger. And again, I will be having something which would be, let's say, I'll start from classical, and then I will do some generalization. So there will be something called omega k, AK will be quadratic term, and then there will be a simplest Hamiltonian, which I would treat, let's say, lambda 1, 2, 3, 4, A1, A2, A3, A4. And of course, lambda always will include delta function of momenta, K1 plus K2 minus K3 minus K4. One may ask, and again, you're welcome to interrupt me at any moment so that I will kind of feel what you know, what you not, what you're interested in. There are, of course, other quartic terms, and there are cubic terms generally in all systems. What is usually assumed when people do classical, at least, wave physics is that this is the lowest order resonant process, namely 1, 2 into 3, 4. So that's this omegas, which stands here, do not allow things like this. So this is not allowed. For example, if you consider gravity waves on the surface of the water, square root of k is one of such examples. And as long as these resonances are not allowed, you can do canonical transformation and just exclude them from Hamiltonian, this respective cubic term. And also the terms which would be like A1 complex conjugated, A2 and 3 and 4 is also usually non-resonant. When this is non-resonant, that you cannot find 3 such which sum into 1 omega. Okay, all this is kind of I mentally assume. If you want more details, I can give you more details, but this is
what
yes.
is the last factor there?
Huh?
What is the last factor there? Omega 1 plus omega 2 is equal to omega 1 plus 1.
I'm saying that I assume when I write this Hamiltonian that this is impossible. This is K1, K2, K1 plus K2. So this all this science goes back to Poincaré, who did celestial mechanics, and he understood that if you have in the Hamiltonian small nonlinear term, you can always exclude the terms which are non-resonant with respect to your basic motion, which is a periodic. So in a zeros approximation, you're in a linear system, you just run with every mode changes in time with the frequency omega, and then you look what nonlinearity could be resonant and remain only this term. So this situation which I'll be considering, there are other situations, but because I want to show you some kind of a wide span and more or less panoramic views, and I choose this because you, in some point, you will see how they closely talk to each other.
Is that omega 1 plus 2? Or
This is omega 1 plus omega 2 not equal. There is no such K1 and K2. This is vectors. Here is omega of K1 plus K2. And this is K1, which tells you that there are no, classically speaking, it tells you that you cannot make spatial and temporal resonance for any three waves. You can find K1 and K2 that give you K1 plus K2 always. And then this K1 plus K2 would have omega, which is not equal to the sum of these omegas. And that means that the term in the Hamiltonian, which were something like such term would be non-resonant. You can find the transformation. I can show you this transformation. You can find it in our book. And there is a book which is, I'll show you this. Vladimir Peter. This is can always borrow it from Vladimir, or maybe there is in the library where you can find all the details and how you do non-resonant terms.
It's also on your website, if I remember.
Yeah, and also on my website there is this déjà vu files that you can always, yeah.
And to get volume 2,
I
you
gave
have to-
up on earning my royalties. Well, I still get some royalties out of it, but they're so minor. And anyway, Russians stole all the files. Yes.
So actually, I kind of read a bit of this book, and it seems that this is what you're discussing is weak turbulence, right?
It's weak turbulence, but it will get strong by the third lecture
Is there a
probably.
reason why you start with a Hamiltonian system in this? So what is the advantage of starting from a Hamiltonian system in this problem?
Well, first of all, waves, because we consider weak turbulence. But moreover, in any normal kind of physical situation which we're interested in, from plasma to the sea, they are really very close to Hamiltonian system. In the sense that when you excite a wave, it really runs like million periods until viscosity kills it. So dissipative mechanisms are really unimportant. So it's a good conservative system, spin waves and solids, etc. So physically we're interested in where the dissipative, and the moment it's non-dissipative, it's Hamiltonian. And that's what my teacher Zakharov discovered when he did his PhD, is that and people at the time, like late 50s, early 60s, they were doing plasmas, they were doing geophysics, astrophysics, and they were doing all types of waves, and nobody talked to each other. The moment they started to write everything in Hamiltonian variables, it was immediately clear that they're doing the same thing. Right? So this is something which, well, the previous generation before me just did this unification, so we can now, because now I can say that here would describe plasma waves, spin waves, surface water waves, just whatever. But systems are really very close to conservative. Okay, so now what we can naturally do, we can be interested in the statistics of the system, because there are so many modes. I mean, this case runs and in this ice a number of particles. So we can look at the distribution of all, let's say, P1, U1 for the system up to Pn, Un. And it's very easy to write equation for this function. So you can easily, let me write it here on this side. So it's d rho dt is equal. So this why I regretted the plagiarism, he has this Haggarom chopped in his room. It might be better.
There is some Haggarom in the middle.
Where this yeah.
There are the white ones. I mean, they're all Haggarom.
White, yeah, almost. Anyway, so I'll keep it for the most important formulas.
So I think there's a request if you can write a little bit bigger, because I haven't figured out how to properly
Okay,
zoom.
so I'll when I write bigger, okay, so what you do, you essentially write that this is d rho dq I, and here what stands as dqi dt, and dqi dt you substitute from here, and then what you do is d rho dp. So what you essentially obtain here is a Poisson bracket of rho with a Hamiltonian, which means that Poisson bracket is you differentiate rho with respect to p, Hamiltonian with respect to q, and subtract the respective things. Because it's a continuity equation, it's you can write it always as a flux of some velocity, and this is 2 n-dimensional vector with a component u dot and p dot. And because of this equation, you discover that what is divergence of this vector, which means that d of dpi of dpi dt plus d of dui of dqi dt sum over all q's, but you don't even need to sum for every I, namely in every plane p q of I, this is 0, just because of this equation, right? So if that would be mixed derivative. It tells you that this equation, even if you're able to solve it, is pretty useless, because we're interested more or less in the relaxation of the system. When we understand that what really we want to go on, we start from some idiotic state or some initial condition, it would do. What this tells you that if you write this equation in the following form, you write it, which is by definition and the gradient means the derivative of all the coordinate x is u t, the whole vector. I just rewrote this equation, continuity equation, as an equation where this is the derivative in a co-moving reference frame, and this is the right-hand side, and this is 0. Which means that if you start from some element of your phase space, you know that your system is in this element, and you want to follow its evolution, what Liouville equation, it's called Liouville equation, tells you that rho is conserved. You can also compute, which is straightforward, entropy, which is rho log rho integral over dx, and it's also conserved. So definitely this equation does not describe any relaxation, and for a good reason, because relaxation is essentially forgetting your initial condition and evolving into some state. And for this, you need some uncertainty. You need to forget some information. You need to project this equation on some part of it, because we are interested in something which is only partial knowledge. So something that will be in this course over and over returning is entropy and information. What is actually where we want? Because if we want to follow every particle, like Maxwell said in his diary, you don't need statistical mechanics, but just you cannot do it. Still, if you want, this is your description. Okay. So in a sense, that's where Boltzmann started. And here I'll be kind of brief, but you want to slow me down, I'll slow it down. I assume that you've seen derivation of Boltzmann equation. So I'll do it kind of fast, but if you want to slow, you can always slow me down. Okay? So what Boltzmann said, forget about all this. Let's just take it, integrate it over dq1, dqn, and dp2, dpn. The result of this integration with the rho of phi of a single, it will be single particle momentum distribution. And similarly, in this case, will be interesting not in the probability distribution of all AKs, AK complex conjugated, but will be interesting only in AK modulus mean value, which we'll call occupation numbers, which would be kind of a direct analog of it. This is the probability of having momentum P, and this would be an average number of excitation in the mode Q, which is also related to the momentum of the wave. Okay? This would be analogous picture. How Boltzmann did it? Well, he took this equation, which now, if you write it, of course, how it would look like. Let's call it N. So let's start from Liouville equation, 0n dt, and it would be something which would be the sum over all I, pi over m. This is the derivative of my Hamiltonian with respect to p, and this would be now d over dq over d. Yeah. What is this? Oh, I'm original.
Well, there's two colored chalk and there's green chalk.
Yeah. I really need.
Actually, can we take this, can we take a 2-minute break?
Yeah.
And can I get some muscle support? Because people are complaining about I think we have a lighting issue here. So on the camera, there are a bunch of people on Zoom who are some of them are complaining about being able to read the formula. I think the issue is that because it's dark enough, the camera is struggling. Can we just take a 2-minute break and move the table a bit closer?
Sure, yeah. Okay.
But it's supposed to be an hour.
A what?
Yeah. I also always
Just a minute.
prefer listeners.
Right, no, there's a bunch of them and they're trying to follow. Now I figured out that this camera can actually
Yeah, but
do a really good count.
then again, if this camera now being so close can take it from left to right.
It can,
Huh?
it can.
Okay, good.
It's $1,000. It's $1,000 camera. It can do.
It's called fish eye, that's what fish eye does. It's really very wide resolution.
Now that cannot see in the dark.
Okay, but there's also in close, because I spend artistic energy of trying to reach you and emotional energy trying to get into contact with you.
Are you saying there's a 1 over R squared?
I expect it's exponential.
Oh, now we're talking about viscosity. Okay.
No, we're talking about personal relationship, and everybody knows that there is some kind of a distance, and after that, everything goes down exponentially. Okay, so now let me get back to you. So you have P over M, D over UIs, and then you have D UI I du over dqi, and u, let me remind you, is the function of a difference. So there will be one derivative with respect to qi, another of qj. So this is the sum over I and j, and this would be d over dpi minus d over dpg. So that's my Liouville equation. And what Boltzmann suggested, let's take it, integrate it over all q's, q1, n, and p's starting from the second up to n's. That's what we'll do. This term would immediately disappear, happily. Okay. Let's call this operator, because it acts on a row. Let's call it theta ij, just for the short notations. So what you essentially obtain over here,
Is there any reason you're not keeping one Q as well?
huh?
Is there any reason that you're not keeping one of the Qs as well?
Well, in principle, I can, but I mentally assume this sentence. This is a very good question. I already mentally assume translational invariance, and I'll be kind of doing a kind of sometimes explicitly, sometimes implicitly. I do assume that it's so. In this distribution, it would be, if I would leave here Q, it will be independent of Q. Okay, so I assume that as a function of Q is just one over volume. Okay, good. So now what I get out of it is this was for rho n, and this was rho n. So now when I integrate, I find out that my d rho of p, well, you can write Q over dt is an integral of theta. Let me write it like this. P theta of Q1 P1 U2 P2 delta function of P1 minus P, this P which stands here, and the integral over dq1 dq1 dp2 dq2 times rho of P1 U1 and P2 U2. Unfortunately, because this term involves two particles, we have what is called closure problem, namely that you will see that your one particle probability is expressed in terms of a two particle probability. Because I'm having right hand and left hand, so now let me do left hand. Namely, how would I encounter this problem here? Here I would write my equations of motion. And apparently the right side would be minus I omega k a k plus I sum of the 1, 2, 3, lambda k 1, 2, 3, a1, a2, a3. That's my equation of motion, which is analog of this equation. A is essentially b plus iq divided by square root of 2. Okay, in a moment, I'll do also a quantum version. So now I multiply it by AK complex conjugated, add to it complex conjugated equation. This term would disappear, and I derive the following equation. That's my nk that I want. And when I get over here, from here, because I add complex conjugated, that would be with a minus signs, I get imaginary part, sum over 1, 2, 3, lambda k 1, 2, 3, a1, ak, a2, a3. Again, I see a closure problem, now expressed in a different way. I wrote the equation on the second moment. It's expressed through the imaginary part of the fourth moment. Okay? So
what are you averaging?
very good question. What I average? If I'm experimentalist, I always average. Well, I can do two averages, but in this case, I always average over time, in the sense that I have my C, I make a snapshot, I do Fourier, I obtain all the amplitudes of the harmonics, all their phases, and then I average over time. Which means that all this about time evolution, which means that this is time evolution on a time scales much larger than my time scale of average. So I assume that there exists this, and indeed, because the interaction is big, In my case, I would be formally considering lambda to be a small parameter, properly normalized. Then it is indeed will be a slow evolution. Okay,
So the brackets can have their own time dependence set by lambda.
bracket, yeah, this is, I mean, the whole idea,
By
Yeah.
brackets, I mean ensemble.
yeah,
Right.
the whole, there are no ensembles here, actually. This is a very good question, what I'm ever sure. There is no ensemble in the sense of Kolmogorov, like you take a different sampling of this. No, well, you can say that my time is what gives me an ensemble, but time also is the evolution which I'm interested in. But what is important here, and let me,
So,
it's good to have different colors, so let me make a border between particles and waves. In both cases, it's a very clear time separation, and this is already good time to appreciate. This rho n is a very fast changing function. Every time a collision, n particle distribution changes, because at least two particle changes their momentum, right? This is a very slowly changing thing. To change one particle distribution, you need many collisions, because you average over n particles. When you ask what is the probability to have this momentum, it's an average over n particles. So you need many collisions to get this. So this is the slowly changing quantity. This analog of it on the quasi-particle level, that omega is very fast. So you have this is very fast changing quantity. This is very slow changing quantity. Okay. So I really, it's okay that we move in such a parallel way, because I'll be at some point I'll switch in one and I'll be doing more particles. At some point I'll switch into waves, but I think it pays to see how this is similar. And in a moment we'll go into quantum and we'll see.
Is that availability of scale separation can depend on the form of omega k that you have?
It's time scale separation that we're talking. So this is it's what is needed for there is essentially that this term is much larger than this term in Hamiltonian. And there are now is a booming mathematical discipline. They got the Simon's grant. Mathematicians now really, I mean, 40 years after we wrote this book, they started seriously to analyze what conditions you need to all this perturbation theory to be valid. And one of the things that we do with Vladimir is particularly is to show him that when you try to apply all this perturbation theory to states which are far from equilibrium, this perturbation theory is non-analytic. This is probably last lecture. Okay. So, but it's a really subtle point, because on one hand, you will see that I would consider some kind of a continuous limit. On the other hand, I consider slow nonlinearity, and which means that I always will be dealing here with some kind of a double limits. Assuming, for example, for Boltzmann particles that they are very dilute, namely it's kind of huge distance from particle to particle compared to the radius of interaction given by the six. But on the other hand, I will be taking thermodynamic limit. Let's forget it and go kind of bird view. I now really want to bird view, but at any moment you can ask me and I'll say, oh, it's very complicated. Okay, so what to do here?
do you assume some ergodic thing? Like
Not
that-
yet.
that-
I'm about to do this. Yeah.
Okay.
This is what I'm now assuming. Okay,
Can you explain again how the closure problem arises on the
the closure problem arises because of this term. Because of this term. So when I want to write, I mean, just technically, you take this equation, this theta is this operator. Okay. So just the fact that you have u, and you just give you this is exactly an operator which acts on this row. So you can integrate over everything, but the moment you are interested in the particle number I, you need particle number j. And you need to sum over all these particle number j's. Okay. So this is the two-point probability. And then Boltzmann did his great step. He said, we are dilute. What means that we are dilute? Which means that our particles are mostly running, not feeling each other. I don't even want to tell you how much mathematical work is still people, already two Fields medals were given for for trying to prove when really it works. But if you're a genius, it kind of works for you. So what you say, let's just say that this thing is almost reducible into a problem. The moment it's reducible, then again, it's independent on the coordinate. So essentially, Boltzmann says that we are really changing this thing when there are collisions. Collisions come because in the state is this U. This U is non-zero. U is usually something like this. U on Qi minus Qg is something like, it change sign, which is kind of irrelevant. Imagine hard spheres, right? This is something very small relatively to the mean distance between particles. This is the scattering cross section. And so I say, if particle came to this point, they came from such large distances. This is all bullshit, by the way. I really want you to feel that this physics, and the moment you try to prove it and say what are really the condition, and we return to it what it means from the viewpoint of more subtle things. But this was a step of a genius. And then, of course, and I'm not going to do derivations that you could say ugly, namely to relate. So what you say is that what you expect to get is a d rho over dt will be some, this is of p. So it says there will be processes in which the particle p meets particle p1, and they would produce particle with a p prime and p1 prime. In such a process, the number of particles with the momentum p would decrease. So you would say that there is some probability of being p1 at the beginning and p prime p1 prime at the end times rho p prime. On the other hand, there could be inverse process in which you would have some particles in which you kind of invert time direction, and particle p appears after the collision. So this would be something which would be W of a, let's call it prime, of p prime p1 prime at the beginning, p and p1 at the end, multiplied by the same things, right? And then you integrate over all dp prime, dp1, dp1 prime. You learned all this, right? So I'm just kind of reminding you. Then what you can say is that you assume, and this is very trivial and yet important thing to remember, that those are results of some mechanics, and they're time reversible. It's not, I really want to stress that this probability of cross sections, they're really time reversible. Namely, this guy is just W of, because when you reverse time, you reverse all momenta, right? So you would get it minus p p1 p prime p1 prime minus. And then you say, but you also assume that your system is invariant with respect to inversion, namely that you can afford to take R and P into minus R and minus P. But then you say that R is irrelevant because I'm consuming translational invariance, and I tell you that if you just do where is my okay yeah what I did wrong incidentally I already jumped over. This was the row 1 row 1 prime, and this was row p prime. Okay, so what you learn is that this is equal to this. And as a result, your Boltzmann equation takes the following form. some W, rho prime minus rho 1 prime. D, P, dp, dp, 1 prime, p prime. So you can take W out. You can consider generalization, etc. This is Boltzmann equation. It's time irreversible because you can prove that if you now take the entropy, where is my entropy? This entropy, and differentiate now by rho, you take this Boltzmann rho of a single particle distribution. So it's a straightforward exercise. I'm sure you've seen it. If you want, I can show it to you that if you compute ds dt, which is essentially integral of W rho logarithm rho, which one? Yeah. So this is what you get if you differentiate ddt of rho log rho minus this. You get this combination, then you can symmetrize it, and you get non-negative quantity, and that what was Boltzmann H-theorem. Let's reflect. What did we do? The only violence that we did to the equation is this step. Time reversibility of mechanics is still there. So time reversibility was obtained over here. Different people kind of interpreted and in different ways. My way to kind of seduce myself into saying that this is what does it mean is saying that if you forget something, then your ignorance would only increase from this moment. The moment you allow any uncertainty, and where I allow uncertainty, this is not equal to this. There is a certain degree of correlation between these two particles. Okay? But then I may ask, what the hell? I mean, this total entropy is conserved. Just, like this. This one particle entropy generally grows. Consider a situation. You start from uncorrelated set of particles. We prepare an ensemble of particles randomly, but on average statistically uniformly distributed in space, with a momentum looking in any direction, absolutely uncorrelated with any other particle, and having distribution, okay, let it run. This tells you the whole entropy of this gas would be constant. This tells you for every distribution you can do the entropy. Whatever rho you have, you can compute it. Then let's ask the question, Sn okay, so are the sum of these entropies equal to the sum of this entropy? Because we, in Boltzmann particularly, and it was very painful for him and to other people around him. It took us 100 years actually to convince ourselves that it's okay. Thermodynamic entropy is extensive. In a thermodynamic limit, we say you can forget about all the other stuff, right? Because essentially we are working with the absolutely short-range forces. For short-range forces, in the thermodynamic limit, entropy must be extensive, right? So what the hell is going on? Are they equal? Is it okay? So already somebody, I really want you to answer the questions, right? Like,
I have a couple of questions.
yeah. I want to answer. So I will,
Oh, what's the answer? What's the answer? The question is why? I mean, I always
no, the
assume,
question was,
well, why? Okay, so
yeah,
if the question is why those things are equal, I think there's a more basic question: is entropy always extensive? And I think the idea is that the probability has to be factorizable.
yeah.
right? I mean, the statistical independence. is kind of
Factorizable
like-
probability is a synonym of
Right.
additive.
And to me, that's already forgetting that you forgot.
Yeah, which means that, but on the other hand, we can say, so what is this difference?
But it's a sufficient condition, but not a necessary condition.
And this is in the modern information series called mutual information. It's what every self-driving car works on. And this is, in a sense, a way to say that there is no contradiction. Absolutely not. It's not a paradox. It's really, I mean, so I hate when I was a student, they taught us that this is a paradox here. There is no, it's sheer triviality, what we are now talking about. And the following thing that you can say the second law of thermodynamics is a conservation of entropy. Because if you really start from a state in which your particles do not correlate, that you have entropy in the state. Okay. Now, when they start colliding, they start correlating. That's what will go on, right? What it would mean? It would mean that this is, by the way, a universal degree of correlation. The difference between the true entropy, it actually makes minus type, because this is strictly less than this. So the growth of it and the growth of it is the same thing, because this is controlled. Okay, so this is a trivial point, and it unfortunately costed us 100 years to get into the triviality of this point. But at least we know. Okay, so now here is the Boltzmann equation, and now
Was there just sorry?
Yeah.
So rho was defined as a the standard sort of a trace over. Like, what was rho defined?
Rho-
not
rho is
conserved.
defined. Yeah, I kind of jumped to it. You define rho if you're a classical person.
Mhm.
How you define rho? You say, here's this my phase space. I mean, 6 times 10 to 23, and I just take any element of it, and then system kind of goes through this element of the space. And then I say the probability to be in this space, if it's not very large element, is proportional to the volume of this element, and the coefficient of proportionality we call density. So this is essentially a fraction of time that you spend in a given region of phase space if you allow, somebody asked about ergodicity, if you allow system to evolve for a long time. You don't even assume ergodicity. It could be that it's still broken into different pieces for which it evolves here, it evolves there. Okay, so rho is defined in terms of a fraction of time.
But you can't really define rho out of equilibrium
Why?
this way because if you,
Well, I can have
unless you have different initial conditions.
first of all, I can have a non-equilibrium steady state, or I need a separation of times. Namely, that I would say my system as a whole slowly evolves from this state towards some stationary state, or maybe towards equilibrium. But my averaging, namely, it really takes a long enough time so that I can introduce rho. It's by itself already assuming time separation.
Okay, maybe I should come clean. The reason I'm asking these sort of definitional questions is, as you were deriving this, I was trying to think, why would Boltzmann want to get into this business? And because the experiments at the time, or at least I imagine the experiments were free expansion of gas, and that happens for non-interacting gas as well.
Yeah, you ask good question. If you read Planck, particularly his private things, he hated all this Boltzmann stuff, just hated. Because there was decent science called thermodynamics. It describes everything you want. And now this guy started introducing probabilities, like gambling, etc. And then it really pays to see how great people, were doing great things without. And then Planck, does his great work about quantum things, and what he does, he obtains this binomial formula. And he hates the fact he wrote somebody. It's like this Boltzmann stuff, which I don't like so much. Okay, so I mean, really, so this is a good question to ask. And why Boltzmann did it? Of course, because he understood that, and Maxwell also understood. I don't know, and this at some point when I'll be retired, I'll go into archive and I'll try to understand to what extent Maxwell really understood. Because Maxwell understood with unbelievable clarity what is actually they were doing. That they were doing information theory and dealing with uncertainty. Maxwell wrote in his diary, if you go almighty in every coordinate, you don't need thermodynamics or statistical mechanics. Okay, so Boltzmann knew it, and other people were happy with phenomenology without all this stuff.
No, but still, so the question I'm asking, maybe I'm just not seeing it clearly. So if I start with an initial condition where all the particles are in that corner of the room and I just let go, we know that over time they will distribute themselves throughout the room,
Yeah.
even without interactions.
Well, that's you're not talking billiards. Of course, you can do
Yeah.
billiards, you can do Boltzmann, Lorentz gas, and you don't need particle interaction with
Right,
themselves.
so.
But if you
where-
want to distribute them with Maxwell distribution over velocity, you need your wall to have a finite temperature.
So they're right, yeah.
Okay.
So just.
Whatever scatter, you can do scattering, you can do Lorentz gas, namely your particle run and they scatter on scatterers which stay somewhere. But if the scatterers don't have temperature, you won't get Maxwell. Okay? On a Maxwell, you need temperature, something need to kick you, or they can kick each other. Okay?
Yeah, I guess the thing that I was trying to understand is that this business of entropy conservation, if you follow the derivation, it depends on the interactions. And so you're saying that wall interactions will induce mutual information.
Yeah, absolutely.
Yeah,
Yeah.
okay,
Okay,
all right.
good. It's enough that particles are in the same potential or scattering with the same scatter, so that you will induce this correlation. Again,
Okay.
so how will be going? I'm talking about 44 minutes. I'll go non-stop for another like half an hour, or we'll make it for another 40 minutes, 45, or we'll make a break for 10 minutes, and then I'll do another 40, 50 minutes. How do you prefer? You alive?
Yeah.
I can go on?
Yeah.
Good, okay, so we'll, we'll finish early. Excellent. So now, what I really, so let me summarize. We came from this to this. This is unbelievable gift of physics to engineering. This is one of the kind of most used equations of physics. Engineers use it like every day 10,000 times, right? Because it's a huge compression. Instead of considering function of so many variables, it's a function of a single variable. From here, you can compute viscosity, diffusivity, many other things. You can compute equation of state also, equilibrium things. Or it's for dilute gas, okay, then you can do a little bit correction to it, etc. Maybe. So this is really, it's not only scientifically, you ask why. You want to compute viscosity, you need this equation, right? Or you want to compute how pressure depends on density, you do this, and you do expansion, you do virial expansion. Let's now try to do it to the left side and see what will be similar and what will be different. Because most of the turbulence I'll be doing here, right? But there will be also some kind of non-equilibrium stuff on the right.
Can you repeat your statement about the connection between, on the one hand, the factorizing the rho into pair, basically assuming interactions are pairwise, to what you said about
It's not assuming interaction pairwise. This is already here. It's assuming uncorrelated particles. That collisions happen between uncorrelated particles.
okay.
And
And on the other hand, what you said about non-extensivity, when there's things are not truly extensive.
yeah, so
What's the connection?
let's really kind of reflect where we are. So we assume that, I mean, this is a true equation, absolutely true. Then we did some violence to it. The violence was replacing rho 1, 2 by rho 1 times rho 2. We get the equation which describes the growth of a single particle entropy. We started from the equation that for m particle, they were fixed. We interpret it as a following statement, that the difference between sum of individual entropies and the entropy of a gas as a whole, and second one by convexity, there is a very beautiful mathematics behind all these things. The second is always strictly, or is always not smaller or equal to the second. So the sum is something which grows, and the two end decrease, which means that the difference is grows, and this difference is the degree of correlation. The difference between sums of entropies, because you are advanced people, let me give you a viewpoint from a totally different perspective. Imagine you're doing measurement by communication. It's all the same. So you have some B, and then you obtain some A. Okay. So you say that there is some probability of B. What is my measure of uncertainty? How much I don't know about B before I started measuring or receiving any signals? Okay, it's S of B, which is minus sum over all values of B.
Mm.
Okay, now I get A. Let's say AI. How much now I know about B? Well, it's determined.
Sorry, A is what? The measurement outcome?
This is impurity in my lattice. This is the reading of a device.
Mm.
Which means they exist in a totally different space. For example, this is something in 10 to 23 degrees of freedom. This is something like I have 15 readings of my space, right? So this space consists of 15 positions, and this consists of some huge. Or it could be other way around. Doesn't matter. It could be a measurement about something. It could be just message through a noisy channel. It's totally general thing.
So A is much lower dimensional than B.
Not necessary. Could be other way around.
But the important thing is that you have a new P of B.
The
As a
important
result.
thing is that what really characterizes this procedure is a conditional probability of having any Bj under the condition of when I get AI. Okay? Now you ask how much I actually learned about B by measuring A. I mean, on average, I measure and measure and measure, and every time there is some uncertainty left. What is the uncertainty left? It's this probability distribution. For every A, I have now this distribution. It's distribution, namely the sum over J of this guy is also unity, right? So now if I take conditional entropy, it's again minus sum of P of B under A log P of B under A. How much I learned, how much I lowered my uncertainty by doing measurements on average. This was before, this is after. So what my information, now you will see as type appears, is P of B minus, well, is S of B minus S of B over A. Okay. Now you can show, and if you want, I can do it next time for you, that this is it's a nice exercise. I just don't because I'm doing kinetics. So I don't worry. But if you really struggle with it, or you can find it in my draft of information series. Okay. This, of course, follows from the so-called chain rules that the P of A and B joint probability AI big J is P of AI times P of BJ under AI. Okay. So now you understand that where this combination sum minus the joint. It's always degree of correlation between them. So in this respect, it's unbelievable that it does not depend on which dimensionalities they live. It's only degree of, and it's symmetric with respect to A and B, right? Which means that if you God Almighty and you know the position of impurities in a lattice, it is as much information about reading of my device as in reading my device about the position of atoms in this lattice, okay? And so at this why the same quantity appears in the Boltzmann differences. Which I love all this because it makes it trivial. I remember, when I was a student, I was sitting in this third year lecture in statistical physics. I hated every moment when they were talking about paradoxes. Because there are paradoxes, like you pretend that something is non-trivial, so you cannot use it. The moment it's trivial, it's a powerful instrument you can use.
So this is how Netflix algorithm works,
Huh?
basically. This is how Netflix recommendation system works. So you have X number of movies and some people rating the movies. entropies.
Yeah.
And how much information you can extract to recommend them the next.
Exactly, yeah. But what really beautiful here is that it's symmetric. It is as much information here about this, even when they live in two different
Is
spaces.
there this SB in the second
Huh?
equation? Isn't it just like SA minus SAB? The after the
Oh, it's just because it's symmetric, of course, it's S of A minus S of AB, absolutely.
Oh, yeah, because in the equality sign, you sum up.
Yeah, sure, you can do this.
No, up. This one you sum SA and SB.
Yeah, it's totally symmetric, which means that this is equal this and this. Incidentally, this all first appeared when Shannon was working with the entropy with conditional probability. People bias did it in 17 something, but people seriously start working with it when they asked what is the entropy of an English language, and then you understand that you just cannot do Gibbs entropy, which is the probability of every letter times logarithm of probability sum over I. It would give you 4.26 logarithm of 26 log 2, 26 letters in English is 4.7 bits, right? A true entropy of English language is 1.4 bits. Namely, you can erase 2/3 of your symbols just here. So people, Shannon started all this. Where does this come? Of course, it comes from correlations, right? So the true entropy is lower because the first thing they started to do is pair correlation. Like, for example, conditional probability of Q, U is U in English language, right? So this, or UQ, other way around. It's always, U is always preceded by Q, unless it's the name of somebody of kin from Africa, which can have. Okay,
And you mention of non-extensivity is basically, you're saying if things were truly extensive, then that difference would be zero. So
Absolutely.
therefore, but it's interesting because, if we think about extensivity, you think about somehow the interactions.
Non-extensivity is always interaction or correlation.
Right. So if you have one macroscopic object, another macroscopic object, you bring them together, and then the entropy is extensive, which is basically
Up to, we say, for short range correlation, etc. This is, but then again, look at what we're doing in 21st century. We were mostly studying non-extensive parts of entropy, namely entanglement entropy and mutual information. Okay, this because, and they usually satisfy some kind of area law or something. They aren't usually volume proportional to volume. That's why but it's not only because we left thermodynamic limit and started to do nanoparticles. It's interesting also for macroscopic things. First of all, because it's conceptually explained to us that there is no paradox in this. Just no paradox. It's trivial. Okay. Good. Let's go now to waves. So I now want to do the same trick. Okay. And good. So let's get rid of particle altogether for now.
So when we're assuming extensivity, are we ignoring, basically we're ignoring correlations, right? Or
Yeah, because extensivity of entropy is a multiplicativity of probabilities. It's non-correlation, and which is nice in the 19th century, but kind of stopped working already. Okay, now let's look here. Where is my yellow? I want to back to yellow. Okay. What is the first thing we can do here? Let's do like Boltzmann did. So, I mean, this is my set of waves. I need to assume now something about the Boltzmann had these particles which were kind of far away. Now I have my waves, and there are complex numbers, there are complex amplitudes. And if I just look at them without any interaction, just every wave, just its phase kind of rotates, and its amplitude does not change. Well, I say, okay, probably there is in my medium in which my waves propagate, there is something which is kind of some noise, which acts on this amplitude independently of each other. So I can assume that these amplitudes, these complex numbers, aren't correlated for different cases, because different waves, they kind of interact with environment differently. Their own interaction is kind of, I can neglect this kind of approximation. Phases for every wave changes so fast, because omega is the fastest thing, that I assume they're just uniformly distributed over phases. It's called random phase approximation. Okay, so in the first approximation, that would be just nk and k1, right? So it's just this times this, only when 2 equal to k, then my phase factor cancel, and I don't have this fast, which would average it into 0. And the same is here, only when k1 is equal to k3, I have a cancellation of this exponent minus I omega k terms. But for this, I need imaginary part of lambda.
Is it an assumption, or is it true that if I start from the system and then I separate into two scales, like in multi-scale analysis, do perturbation theory, integrate the fast degrees of freedom, I get the same average? Is it proven, or is it an assumption?
It's usually work very well until you do the first, sometimes second step. If I would use this jargon of theoretician, one loop is okay. And two loop, you start seeing how much it depends what is actually this distribution. And this would be partially subject of this course. Okay, but in principle, you can do it in a many different ways. You can add here some random forces and also some dissipation, like you put it in the contact with the thermostat. Then you and this is something which in a moment I'll show you. It's kind of and then you can average over the statistics of this Gaussian force, assuming this is what I'm mentally doing, saying that they are close to Gaussian, etc. Okay. Well, we can see how it works. If you really go from a k of t integrated with I omega t dt, you would define a k omega. Right? This quantity from here would satisfy the equation omega k minus omega minus I gamma aq equal to fq, which is the Fourier image of this, and gamma is already here. So plus I sum a lambda. So you can take this equation and solve it perturbatively, namely, you say that your AQ is f, well, it's actually green function, so let me write it as f g naught plus, and then you would have f term, and then you would have f terms, something like this. And then you just take this series and multiply it. And you can get any perturbative expression. This is one straightforward way. And Vladimir always laughs at me, but some computations which I really don't trust, I repeat in this idiotic way, which I learned 40 years ago, and I'm still doing it pretty fast. And of course, modern people just do it with a pass integral. Anyway, so let's. And because f is Gaussian, then you would have the first term you would get Gaussian term, and then all the cumulants.
Okay, but in principle, you could, this is all equations of motion. You could say that I have a very specific initial condition.
Or
I can do perturbation theory on the dynamic.
just the same. You do initial condition, which are random Gaussian field. You do Laplace, you get the same
Right,
thing.
exactly.
Absolutely. So this is you can do it kind of, there are like 20 ways and they all correct. But so now let's assume that there is quantity.
Wait, just to finish that, they're all correct at low orders in perturbation theory, but then if you have singularities, how you,
Which singularities?
well, I mean, if something, I guess what I'm saying physically, these are different processes. One of them is an inhomogeneous differential equation with a forcing, the other one is initial condition. So I kind of feel like physically, because physically they're very different systems. at late enough times, the
No
dynamics will
idea.
know.
I have no idea. We all know that they work pretty the same close to equilibrium.
Or in perturbation, I would
I'm-
think that.
I'm almost sure that there are big surprises, big beautiful surprises far away from equilibrium in terms of what you've got by imposing this infinitesimal random kicks or starting from initial conditions. If you want, maybe at the third or fourth lecture, we talk about it. Because evolution starting from random initial condition would go non-stop very far away to a very correlated state. The entropy would be parametrically lower, which would be some kind of a fractal distribution in phase space. Nowhere close to this state. Okay, but what I now want to show you how the same thing, which we did for Boltzmann, would give totally different answer for waves, right? So in the first step, I would assume that there is an imaginary part of it, and then I can use just the same breakdown over here. So what I will get the equation, which on the jargon, which plasma people did it first, and get a huge surprise. So it looks like this. It will be mk sum over q and q s k do. And s is antisymmetric because it's an imaginary part of. So which tells you, well, it's kind of strange. So you have a Hamiltonian which has a here an imaginary part. Well, imagine that you.
But this Hamiltonian will not be Hermitian.
Huh?
But this Hamiltonian.
Will not be Hermitian. Yet, I mean, in plasma, you get this equation for the function. M would be essentially a square of electromagnetic field is related to propagation of linear waves of plasmons. And this would appear because they have what is called induced scattering on particles. So you would have an electric wave which changes locally density, and this change of density changes the refraction index for this wave. But it's something which you really need kind of plasma close to isothermal, namely this perturbation, they are dissipative, they strongly dissipate. You can also get it from some kind of magnetic field, etc. You need a breakdown of time reversibility in a sense. But still, this is not a true kinetic equation, as you will see in a moment. You need something else. So first of all, it's really time reversible, right? We just consider two mode version of it, like dn1 dt with dn1 n2, and dn2 dt would be minus n1 and 2, right? Well, we know what it describes. It describes the evolution that everything would go to n1, right? So if you would just look at n1, n2, it's just this you have one fixed point, this you have another fixed point, and this point is unstable, this point unstable. Okay, that's what you will do. Now it's irreversible. Okay. And then people who did it, let's say, okay, but then now we may try to describe it, interaction with an environment, and what they were really doing, because they were applying it to plasma, they were saying, let's have some gamma, which could be, you know, positive part and negative part. Which means that you get some kind of a beam of, that was all related to thermonuclear fusion, but essentially it's kind of saying that you have an instability in some region of K-space and you have a dissipation. So you would expect that this guy would provide you kind of a, and this is a typical turbulent type situation, right? So you would get here excitation, this nonlinear term would provide it over here, and you get a steady state, right? And your steady state is when your gamma is equal to this. So this is 0. And then they discovered an interesting thing, that if you divide it by NK, then it's a Hamiltonian equation. Something which I still remember how these people were shocked. So
Wait, I'm sorry. How did you write that equation to begin with? Because it was
no. So you are. So I mean, I look at this and I did the first thing, Boltzmann type. I say, imagine that you have an imaginary part of your lambda, let's call it S.
Oh, you made lambda itself imaginary.
Lambda itself is imaginary. Only in this case, I have this first trivial, Gaussian part of it giving me
Got
non-trivial
it. But the
contribution.
physical lambda is real because that comes from
No,
interaction.
not necessarily. What I'm saying is this is an equation which appears. There is cases with magnetic field. There are cases with induced scattering. So it's in a sense interaction of particles through something which is strongly dissipating.
Okay.
It's when your green function in kind of imaginary part is stronger than your
Yeah.
omegas. Okay. So this is a pretty physical situation. And in particular, this is an equation which really very well describes the evolution of, let's say, electromagnetic waves in plasma, where the interaction is through the fluctuation of particle density, which locally change refraction index. That's good. What this equation is really can be written like this: that is a sum over Q and dH over dQ dz U. So let me call it dzk over dt. So z k is the logarithm of mp. That's what entropy is made of. And skq. And the Hamiltonian is, of course, sum over, where is my Hamiltonian? Over k exponent minus zk, this is just my, and then it's a sum over k and q gamma q z u r k q and r k q is just an inverse to s k q. So you can treat this as a matrix and inverse matrix of it. So what is important here? This is the skew symmetry. It's a really symplectic structure here. This is a Hamiltonian, which means that this is conserved. So even though it's irreversible, that it cannot really describe your evolution to whatever you want system by your external forces. And this is something, incidentally, which was an important practical result for thermonuclear things. But it tells us that what looks superficially similar to the Boltzmann step is not. Because you're right, it's really based on some very, very special case of imposing irreversibility on a Hamiltonian level. So this is not a true, it's called induced scattering equation, but it's not a true kinetics in a sense, which would describe an evolution. But the Boltzmann equation, you could add any sources of things and it would evolve into respective non-equilibrium state. Okay. So what now is clear from here, this was actually a thing which I wanted for Vladimir, but I'm not sure that he knew it. So now let's go next step.
Is that in your book also or no?
No, it will be in the second edition. I already wrote it in the second edition, but it's not in our.
Wait, there's a
It's
second
not in our
edition?
book. I don't know why, because when I was a student, I discovered a version. I was so impressed by this thing, which was just obtained for plasma, because what it actually means is there are other small terms which really describe the relaxation to equilibrium, and as a result, the relaxation in plasma very often happened on a very, very large time, which had kind of big practical things. So I kind of invented a simple generalization for three-wave interaction, etc. But no, I don't know why we didn't. Yeah,
So wait, but just, can I just?
there's no turbulence here.
Yeah, this is too
I
boring.
wrote it when I was 32. I mean, I was interested only in turbulence. Now I see the kinetics much wider.
Yeah.
It's kind of just way narrow.
Okay, I'll ask my questions about it later. Okay, that's fine. Go ahead.
Good. So now let's say that imaginary part of lambda is 0. So there is no such trivial thing. We need to go to the next order. Namely, so from now on, I say that this is 0. And which means that the Gaussian decoupling here so my imaginary state, okay? This is really non-Gaussian part. I really need a formula here. And of course, there are two ways to do it. You remember that one way is this, that you write A as F G naught plus G F F F. It's actually enough. And then you just substitute it here, so you find out that when you, at every A, you substitute this term, and this is Gaussian field. This is the Gaussian force in Cartan, right? So when you substitute these terms, that would give you 0. So then you need to substitute at least in one place this cubic term, right? So you would get something like F, 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 and this F, 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 right? And this was already 6. And so when you add, well, there will be 3 complex conjugated. So after averaging, you will get something like N, N, N. And when you substitute into 4 different positions, what you essentially get, and again, because remember, let me write it again, the AQ K omega is FK omega GK omega plus lambda lambda G plus F. So already this will give you extra lambda, and this also has lambda. So what you get as a result, you will get the sum over 1, 2, 3, lambda K 1, 2, 3 squared. And it would be 4 different terms corresponding to where you put your cubic term, right? So there will be n, k, n1, n2 plus n k, no, n k, n2 and 3 plus n1, n2, n3 minus n k.
So are you averaging over Fs?
Huh?
Are you averaging over Fs? Did you perform the average over F?
Yes, I assume that F is a Gaussian random field, and probably I would need to take it a little bit. So I assume that this is some Fk of t, Fk prime of t prime is delta function of t minus t prime, and it's Fk somehow dependent on k, and I assume that Fk over gamma k is my nk. And I take a limit f going to 0 and gamma going to 0. That's a formal thing. But then again, you can do it in.
And what does G give you?
Well, G is everywhere here is just 1 over omega minus omega k minus pi gamma k. So when you take limit of gamma going to 0, you would get a delta function of omega k, which I am about to write it here.
So that's energy conservation.
That's energy conservation, exactly. So you remember lambda contains delta function of momenta. Now, when I finish doing this, this is nk, and this was n2, n3, n1, n2, n3. Now nk, n1, n2, nk, n1, n3. And I will have delta function of omega k plus omega 1 minus omega 2 minus omega 3. This equation was derived by another PhD student. Everything was done by PhD student, incidentally. He came to Sommerfeld to do PhD, and Sommerfeld left to, round the world trip. So he was totally alone, and so was talking to really good people around, including Dow and Heisenberg. So this was his one of the results in his PhD. Okay, this is a kinetic equation, and it looks differently from Boltzmann equation. First of all, it's cubic in n's, right? And it has a similar sense because Boltzmann equation were also true when the colliding particles, the sum of momentum before collision was the sum of momentum after collision, and the sum of any before collision. And here I also have delta function of omega and here. So now what I want to do as a last thing today, and then we'll start next week, continue. I want to now derive a quantum version of it. And then you'll see how it bridges between these two things. Okay. So let me do it here.
So you have taken a thermodynamic limit somewhere, right? When you're writing.
No, No. I impose statistics in this way of derivation by my external force F, which means that my external thermostat or whatever gives me this kicks assumed to be some kind of a thermal equilibrium which provides Gaussian statistics, which essentially requires thermodynamic data. But within this formalism, technically, I can consider any finite number. But when you look here, you say, well, come on, you write delta function, which means that you already need a dense enough set of resonances so that for your case, imagine they're on a lattice.
Yeah.
This would give you some surface. And this surface must come close enough to the sides of your lattice. This where Fields medals are given. This where mathematicians now work. It's a very non-trivial thing, particularly combinatorics of really how you need to take L to infinity, which is your distance between your nodes in K space, to provide for dense enough set of resonances so that it gives you meaningful acoustics. You don't want to open this one.
But physically, you are okay with quasi-resonances? Or...
Physically, we apply it to 100 nodes and it works surprisingly well.
Okay.
But it's not that we, and mathematicians get their all great prizes analyzing the validity of this equation for n close to thermal equilibrium. The only thing which asks how this equation valid, namely what are the next terms, is Vladimir and me now, and there are no other people who really ask this uncomfortable question: what is the next term? Maybe it's much larger, right? Because we know that for thermal equilibrium is kosher, namely the next term could be small, and there are some conditions in which you.
So next term not in the expansion.
Next term, which means lambda cube term.
Okay.
Because you can substitute here FFF in here F and F. Okay, so you can get F, and here 3Fs and here 3Fs. With extra lambdas. It would give you extra next term, etc. We'll talk about it.
Actually, just one question connecting to what you said earlier, that so you kind of assume the square root K, which removes this cubic term, right? So let's say if you have like this gravito-capillary system, which is a linear combination of.
For capillary system, you would need a cubic term. You cannot get rid
But
of it.
so for that cubic term, this quartic term is the next term according to your calculation, and then
Yes.
you'll see the same physics at the
Yeah,
quartic.
people who do, for a C turbulence, you actually don't care about capillary waves unless you start asking how you fit plankton by breaking waves and all this. This really depends on capillarity. But when you do experiments in the lab, people usually write cubic term, which is from capillarity. Capillarity is something that omega is K 3 times. It's also non-analytic, incidentally. That's a very interesting question, but it's something which is resonant for 3 waves. Let's not do it. Okay, let's still. So what I now want to do, I want to do quantum, and we'll end with it. So what I want to do, I want to do the following thing. I say my Hamiltonian is H1. Very rarely in my life I write H1. My teacher would be proud. And then you take this lambda 1, 2, 3, 4, A1, A2, A3, A4. Okay, and of course delta function is all the bells and whistles. Okay, now you say, okay, good. So generally it's again, I assume that in some sense this is a large and this is small. Namely, essentially, I am having a quantum problem with oscillators. So this is a set of independent oscillators in the first approximation. For every K, I have independent oscillator, and I can just characterize it. There's respective energy, AK is H omega K, NK plus 1/2. So this would be kind of my occupation numbers now. So I will characterize my system in terms of non-interacting occupation quantum numbers. And then I would say that now in this representation, I know how my operators act, right? So if I act on n k minus one, I would get n k, and this is equal to square root of n k. And at the same, if I would act from a k on n k, then I would get n k minus one over here. So now I'm working with these states characterized by these quantum numbers. Incidentally, note that I'm not asking about phases, which is my way of doing random phase approximation, right? Because the moment that I have a definite n, I have indefinite phase. So it's a very, very much in parallel. And then I'm saying that what now I need to do, if I really want to compute d in k over dt, and I am in the first non-vanishing Born approximation. So what I need to do a square element and compute three, and I need to take my A1, AK1, A1, A2, A3, and this would be something that would increase the number of things in K, and then there will be something which would be complex conjugated, which would be AK, A1, A2, A3, and when I'll be acting on states with NK, N1, N2, N3, each one will be acting independently on it. And I'll be just using this matrix elements of this operator, which apparently is clear that what I will get as a result is the following things. Is the sum of
So here you have assumed a quartic potential on top of a quantum number.
this my Hamiltonian, which means that I choose my quantum state according to non-interaction particle, and now I compute in this representation the matrix element of my interaction, and I get in the first non-vanishing order a evolution of the things which would give me essentially the following things. That would be lambda k1, 2, 3 squared, energy conservation.
So just to make sure I understand something. So your Hamiltonian before forcing is particle conserving, but your forcing is actually particle production.
You mean in this?
Yeah,
Yeah.
it's particle production. You're sorting in and out.
I really need this limit.
Right.
Or I can again. With equilibrium, it's nice and easy because I can have detailed balance. Namely, for
Right.
every k, I can have. But in non-equilibrium, but then again, this f and gamma is not my. It's not what produces turbulence. It's my technical device to impose Gaussian statistics. If I want turbulence, I need to add another forcing somewhere and another dissipation
Right.
somewhere. They would
No, I understand, but
definitely
at the end of the day, I guess what I find mind-boggling is that you have in equilibrium, there are no imaginary correlators, right? It's a current, right? So you're basically producing a state that has some flux through it.
yes,
Right? And
that's what interaction does. Yeah.
well, but
Well-
then things can somehow calm down and forget about.
No. If
You have phase space. So n of k, maybe this is a more direct way of saying it. So right now you wrote down, right, the n of k dot is a current. So every k point, there's a current moving.
yeah.
And this current, I think by particle conservation, because you do take forcing away, this current has to be uniform in k space.
For steady state. Yeah. We'll talk about it.
So there's stuff moving through the system in
Yeah,
steady state.
But well, it's actually moving in two directions because there are two integrals. That's what
Right, okay, right.
next lecture would
Okay,
be
fine.
would be
Okay, I
spectral
won't jump.
classes. Let me just finish the equation. So what I really wanna finish is that I will just kind of write this integral. So I would say nk1 n1 plus 1 n2 n3 minus n2 plus 1 n3 plus 1 and k n1. And even because if you look and you will see that the terms of the force of the nk n1 and 2 and 3 and k n1, they all cancel out. So essentially I can write it like this. So this is the quantum kinetic equation. And now, if you take its limit when n much larger than unity, you get this equation because you neglect these unities, and you'll see. And when you take your n much less than unity, you forget it, and you get Boltzmann equation, n2 and 3 minus nk and 1. Okay? So it is this second order of really taking this real and accounting for cumulant over here, what is equivalent to the Boltzmann equation in the quantum limit and to the Peierls equation in the classical limit. And first of all, it tells you that this equation has it all. Because when we'll be later talking about wave turbulence, the C storm, which is described by this equation, Boltzmann equation has also flux spectral solution. For example, you can irradiate a metal with a very strong radiation, and it produces very high momentum electrons. So they produce lower and lower and lower momentum, and those essentially will go into lattice. This is also type of a cascade. Cosmic rays, you have cascades. That's what Landau and Rumor working at 30s. You have cosmic rays with very energetic particles, and they start producing cascades of particles, which is very much, and they describe a Boltzmann equation, and it has turbulent solutions. But this equation has it all. Namely, it has both limits, right? Of course, it's not scale invariant. It's only scale invariant in one limit or scale invariant in another. So I want to finish at this point. So let's reiterate what we did today. We started kinetics, classical kinetics of particles, classical kinetic of waves, the equation which breeds them all, and we also discussed that there is nothing non-trivial here. It's really, if you come from n particle description to one particle description, you lose some information, you get equation which is time irreversible, entropy production. If you have some uncertainty, your uncertainty will only increase. If you do all in particle description, it's Liouville theorem, kind of you know everything, you know, if you know everything, then you know everything. If you know part of it, you know less and less. But this equation are workhorses. They are really people, that's what we'll be working with them for next lectures. Okay. Next lecture, yeah. Thank you for
Next lecture is on Thursday at 10 o'clock.
on Thursday at 10 o'clock. Okay, next Thursday, yeah. And I have a hotel for the next week.
I believe so.
Yeah.
Are these lectures written down somewhere? Is it printed somewhere?
Yeah, you know, I'll probably there are pieces. I have two books. Well, I have four. I have two books. One is this book on wave turbulence, and another is a book which is about Utopia, but it's already on my web page. You know, just everyone can download it. It's called Information Theory. So some things are in one book, some things are in another book, and we'll probably have some site or so. I will be just giving notes which one is which, because it's the first time I'm giving this kind of, you know, a synthetic course between the things. But it's really very good because you're giving me so good feedback. So I'll now go and change a couple of places in this lecture.
So
Yeah.
you're assuming that this lambda do not produce anything like some condensate or.
It will, of course. Sure, absolutely.
Oh, okay.
That's the next lecture.
But then the starting point is not correct for like the vacuum, right?
Well, there is no vacuum here in the sense that, well, you can say that my vacuum is just thermal equilibrium. Well, I'll be interested in is a very turbulent state of the medium.
Oh, I meant the quantum part.
In the quantum part, yeah. In this point, I assume that there is no condensate because otherwise it would totally change this kinetics. I would need to put a condensate, it would produce immediately three-wave interaction, etc. But I'll talk a little bit about it. I mostly won't be doing quantum, but I really wrote this equation quantum just to show you that analytically you can go from this equation both to Boltzmann. I think it's conceptually important, but mostly I'll be working with this classical, maybe a little bit with Boltzmann. Good.
It might be like a naive question, but I think you absorbed the momentum delta function in the lambda factor.
Yes.
So when you expand the fourth order cumulant in lower orders, do you like have additional delta?
Yeah. It's usually, you know, when you go to next order, there is like every lambda comes with its own delta functions. Yeah, it means that it's always kind of you add some integration, but then you also add an extra delta function. Okay.
Any, maybe I should ask people on Zoom. Anybody on Zoom wants to ask anything? I see that Alex, you unmuted yourself. You getting ready to ask a question?
Was muted all the time. So,
Oh, okay. All right, never mind.
so far, no questions. Okay.
All right,
Okay.
okay, I guess then we'll wrap up.
Yeah, and incidentally, if somebody kind of has any question, you can also send it by email. It's easy. You just Google Gregory Falkovich, you get my homepage, and there on my webpage is this information series notes. Send me email so that by next Thursday I'll prepare the answer. Okay.
Okay.
Question, so it might be slightly, you want to close that out and.
Oh, you want me to?
I understand the question. Yeah.
Well, that's